Mountain belts, a group of mountain ranges with similarity in form, structure, and alignment that have arisen from the same cause, usually an orogeny, expand for miles and miles, hundreds, even thousands of kilometers. Mountains are something that we see for just a short moment in time, but they are something that took millions of years to form. So, how do mountains form? And how do ancient mountains form? The size and age of mountains make their origin story hard to understand, and ancient mountains have an origin story that are even harder to understand. To better understand the formation of mountains in ancient mountain ranges in the geologic past, we must first understand plate tectonics. In 1915, a scientist named Alfred Wegener proposed the theory of continental drift. He believed that the continents were not always in their modern position after realizing that the coastlines of different continents fit like puzzle pieces. His idea of continental drift was controversial, however, because he was unable to explain why the continents moved or how they moved. Eventually, paleomagnetic studies revealed evidence for the movement of the continents. First, the magnetic North Pole seemed to wander all over the globe, meaning that the plates were moving, or the North Pole was. Next, a series of seismometers showed that active geologic features, for the most part, aligned with distinct belts which outlined the tectonic plates. Lastly, a striped pattern of magnetic reversals was found in oceanic crusts. This was evidence that the Earth went through several magnetic reversals in which the North and South poles reversed for a period of time. This was proof that the lithospheric plates had to be in motion. Plate tectonics is a theory explaining the structure of the Earth's crust, and many associated the phenomena as resulting from the interaction of rigid lithospheric plates that move slowly over the underlying mantle. This process causes the continents on the Earth to drift and collide, rocks to grind and scrape, mountain ranges to form, and also causes earthquakes to tear land apart. There are 3 different plate boundaries associated with plate tectonics. The 3 plate boundaries are convergent, divergent, and transform. In convergent plate boundaries, 2 plates collide with each other. In divergent plate boundaries, 2 plates separate from each other or they move apart. Finally, in transform plate boundaries, 2 plates slide past each other. Since its emergence in the 1960s, plate tectonic theory has gained widespread acceptance as the model of Earth's processes. Let's focus on convergent plate boundaries and see how they play a major role in the formation of mountains. Convergent plate boundaries are known for their creation of subduction zones. Subduction zones are where one plate, the densest one, subducts or dives underneath the more buoyant plate. There are 3 types of convergent plate boundaries in which plates converge. Later on, I will focus on just one of these convergent boundaries. The first type is continental-continental. Continent-continent convergence creates some of the world's largest mountain ranges. Magma cannot penetrate this thick crust, so there are no volcanoes, although the magma stays in the crust. The second type is oceanic continental. A subduction zone is formed at the convergent plate boundary where one or both tectonic plates is composed oceanic crust. The denser plate, made of oceanic crust, is subducted underneath the less dense plate, which can be either continental or oceanic crust. Oceanic is the third type of convergent boundary. The features of a subduction zone, where an oceanic plate subducts beneath another oceanic plate, are the same as a continent-ocean subduction zone. An ocean trench marks the location where the plate is pushed down into the mantle. In this case, the line of volcanoes that grows behind the upper oceanic plate is an island arc. 3A depicts a continental oceanic convergent boundary where the denser oceanic plate slides underneath the continental plate. 3B depicts a continental-continental convergent boundary where the most dense continental plate slides underneath the less dense one, resulting in the creation of mountains. 3C shows an oceanic convergent plate boundary that results in the formation of deep ocean trenches and island arcs. Let's take a look at what a mountain is. A mountain is a large landmass that towers above the surrounding area and forms a peak at the top. The UN Environmental Programme's definition of mountainous environment includes any of the following: elevation of at least 2,500 meters, elevation of at least 1,500 meters with a slope greater than 2 degrees, elevation of at least 1,000 meters with a slope greater than 5 degrees, elevation of at least 300 meters with a 300-meter elevation range with 7 kilometers. The diagram to your right shows you that Mount Everest is the tallest mountain, standing at 8,848 meters in Asia, and the smallest is Townsend Mountain, standing at 2,229 meters in Australia. Now we must understand why it is hard to figure out how ancient mountain formed. As is evident, there is a close relationship between plate tectonics and the formation of modern mountain belts. What about ancient mountain belts? It is difficult to explore the ancient episodes of mountain building because the oceanic crust is destroyed at subduction zones and rarely survives for more than 200 million years. This makes seafloor spreading evidence from the geologic past hard to find. The key to unlocking the ancient plate movement was finally provided by the Canadian geophysicist J. Tuzo Wilson. Canadian geophysicist J. Tuzo Wilson came up with the Wilson cycle. The Wilson cycle was a proposal by J. Tuzo Wilson that offered an explanation for how the Appalachian Mountain Belt of eastern North America and its continuation as the Caledonian Belt in Western Europe formed by the destruction of an ocean that predated the Atlantic Ocean. According to his model, the Appalachian Caledonian Mountain Range formed over 500 million years ago. Wilson found that there were 2 different fossil assemblages found in the rocks of these mountains. One was called the Pacific Realm, and the other was called the Atlantic Realm. The differences between these fossil assemblages meant that the shallow marine sedimentary rocks in which they occurred must have been separated by an ocean at the time of their deposition. The Wilson model is as follows. Step 1. A continent rifts when it breaks apart. Step 2. As spreading continues, an ocean opens, passive margins cool, and sediments accumulate. Step 3. Convergence begins. An oceanic plate subducts, creating a volcanic chain at an active margin. Step 4. Terrain accretion from the sedimentary wedge welds material to the continent. Step 5. As 2 continents collide, orogeny thickens the crust and building mountains. Step 6. The continent erodes, thinning the crust. The Wilson cycle determines how the oceans open and close, but what determines when they do? A larger tectonic cycle called the supercontinent cycle answers this question. Even though the ancient oceans are likely to be destroyed after subduction, Tuzo noticed that the continental shelves and the magmatism associated with them may be preserved. Continental crust is a poor conductor of heat and acts like an insulating blanket. This causes the heat underneath a supercontinent to build up. Magma is generated as the heat rises and the supercontinent bulges, then cracks. The magma fills the cracks and the supercontinent is progressively pulled apart. Future supercontinents, Pangaea Proxima and Amasia, are predicted to assemble within the next 50 to 250 million years.